We can design complex mathematics perfectly on paper, but physical reality is naturally chaotic and resists precise instruction. Bridging the gap between what an engineer wants a machine to do and what the machine actually does requires a specific architectural layer. It is a hidden framework present inside almost every piece of modern technology. Consider an air conditioner sitting in a window. When you set the dial, the unit's entire objective is to take the ambient room temperature and force it to match your predetermined target. We see the same process when a heavy automobile accelerates. The internal elements of the vehicle have to overcome mechanical friction and inertia to force thousands of pounds of resting mass to hit a target speed, say exactly 100 kilometers per hour. Or consider a standard elevator moving between floors. Its objective is to calculate and halt thousands of pounds of upward momentum so that the car stops exactly flush with the desired level. These are all applications of a formal academic definition. A control system consists of specific subsystems assembled strictly for the purpose of controlling the output of a given process. This specific arrangement of subsystems provides the architecture required to automate physical reality. While an elevator and an air conditioner operate on entirely different physics, the control theory driving them shares the exact same foundational architecture. Every control system begins with the mathematical or physical command given to the machine. This is the input, or the stimulus. That command flows directly into the system itself, the physical mechanisms built to process the instruction. The system then generates a physical reaction, known as the actual response. But because of mechanical imperfections and environmental physics, the actual response produced by the machine rarely matches the desired response the engineer actually wants. To fix this, the architecture requires the system to continuously measure its output and route data back to the beginning. This feedback loop feeds into a comparator mechanism, which sits beside the input and continuously judges the output against the command. This creates the central mathematical concept of control theory, error. It is calculated by taking the desired response and subtracting the actual response. Once that specific error value is calculated, the rest of the internal processes adjust their behavior until that specific number drops to zero. A control system is an active, continuous mathematical loop, relentlessly hunting for zero error. We build these complex, self-correcting loops to solve 4 specific physical constraints. To see these constraints in action, we can use a massive structure like a deep space radar antenna as a case study. The first specific constraint is power amplification. Imagine a human operator trying to manually push this multi-ton dish to a precise coordinate. The human input, physically turning a small command dial, contains only a tiny fraction of the mechanical power required to move the steel. By placing a control system in the middle, electrical motors read that weak input signal and amplify it into massive torque for the output. The second constraint is remote control. Because the control system reads signals, the input dial does not need physical connection to the machinery. This allows control systems to operate in dangerous environments, like robotic arms handling materials inside a radioactive containment chamber where human presence is impossible. Without power amplification and remote operation, humanity's engineering footprint would be limited by the reach and strength of our own bodies. The third constraint is the convenience of the input form. Turning a physical dial generates rotational kinetic energy. But the system moving the dish might run on electrical currents or hydraulic pressure. The control system translates your instruction into the necessary physics. Pressing a button on an AC unit is physically disconnected from the thermodynamic process of cooling air. The system handles the translation for human convenience. The fourth constraint is the most critical: compensation for disturbances. Suppose the dish has reached its exact target angle. Suddenly, high winds slam into the structure, physically bending the metal and forcing the antenna off target. The human operator hasn't touched the input dial, yet the physical response is now mathematically incorrect due to environmental noise. Because of its closed-loop architecture, the system instantly detects the change in its own output and calculates this newly introduced error. The feedback loop triggers the motors to increase torque and push back against the wind, entirely independent of human command. We do not adjust the input dial to fight the wind. The machine is designed to reject the disturbance internally. This internal recognition of environmental chaos and the autonomous response to it defines the control system. Whether it is amplifying torque, bridging distances, translating energy, or fighting off a storm, the architecture shares one goal. It takes an input, measures reality, and drives the mathematical error to absolute zero. Predicting exactly how fast or how stably a machine reaches zero error requires stripping away the physical imagery of motors and antennas. To analyze time and frequency response, engineers map these physical components into mathematical transfer functions operating in the Laplace domain. We test if a system will safely settle or oscillate out of control by applying absolute stability metrics, like the Routh-Hurwitz criteria. For the most advanced machines, engineers use state-space analysis. When dealing with robotics or aerospace vehicles with dozens of intersecting inputs, the block diagram is replaced entirely by matrices of state variable equations. While the calculus and matrix algebra required to map these systems are rigorous, they are tools to describe the physical realities we've discussed today. A matrix equation is simply the mathematical guarantee that an antenna will point exactly where we command it, no matter how hard the wind blows. The feedback loop and its relentless pursuit to eliminate error is the unshakable bedrock upon which all complex automated engineering is built.